So today we discussed the power rule, also known as the Mr. Boyden, why did you tell me a week ago, because that would have been really, really nice a week ago rule. And it simply goes like this. Rather than plugging in our difference quotient, we find a pattern and we do a bunch of those. So what we realize is that all that's happening when you take a derivative of some sort of polynomial, something x to the n, is that little guy, the exponent, is coming down in front, and the power is being reduced by 1. We saw that in our last activity with the graphs, where it was a cubic and the derivative would be squared, or if the original function was squared, the derivative would be linear. It decreased the degree by 1. And so we see that here as well, and this is the formalized notation for it. Just to help you remember, it's sometimes called the slide and, no, we'll not add, slide and subtract rule. And the reason some people would say that is we're just sliding the power down in front, boom, there it is, and we're subtracting 1 from the exponent. So let's take a look at what it looks like in practice. We'll get through a couple of examples. On this first one, pretty simple, pretty quick. Bring the 3 down in front, subtract 1 from the exponent, and now you have 3x squared. Pretty easy, a little easier than a difference quotient. That's it. Keep going. Same thing here. Now we just have a coefficient in front. Slide that down in front, subtract 1 from the exponent, and you get 6x. And they asked us for some derivative values, some f prime values. No big deal. Plug them in. 6 times 0 is 0. 6 times 3 is 18. Okay, so now these just got really, really quick and easy. And let's continue. All right, sometimes we're going to try to trick you by putting things in a little bit different form. And the thing that's going to be tricky on this one is that little radical right there, because that doesn't look like a power. But what we have to realize is that can be rewritten as an exponent, like this. So it's still 2/3, but then it's x to the 3/2 power. Okay, remember that root is a 2. So then the rule does apply. We can pull our little 3/2 down in front, subtract 1 from the exponent, 3's cancel, 2's cancel, hey, that's nice. And so now we have an x. See, 3/2 minus 1, that would be the 1/2 power. We can absolutely leave it like that, or if you really have a strong preference, you can rewrite it as square root of x. Both of those are excellent. Okay, one more. And one of the things we want to focus on here is we've got the trick where we can, if we have a bunch of different terms, we can look at them one at a time. Think of this as 4 different questions. And then we're not concerned with multiplied constants, or coefficients as we sometimes call them. We're just going to treat them like they don't do anything, because in a derivative, we preserve them, but they don't change anything in our process. So let's go ahead and get going on this one. Pull the 2 down, minus 1. Pull the 3 down, minus 1. Ooh, what happens there? That's a 1. Pull the 1 down, minus 1. And then constants turn into 0. So let's write out what we have. We have 6x minus 15x squared plus 2. And that is our derivative, dy dx. Okay, now it's done. Okay. Sometimes we're going to get something real exciting, a real exciting piecewise like this one. So we're going to talk about how to do that. We're just going to take it one piece at a time. Okay? So first piece, what I've got, I'm going to write this as f prime x equals, let's see, pull the 2 down, subtract 1, that turns into 10x. We'll come back to the domain conditions or the domain restraints in just a minute. Let's go down to this one. Bring the 4 in front, that becomes 16x cubed. Pull the 3 in front, that becomes 9x squared. Constants, they died. So constant is gone. Now let's deal with our domain restrictions. I'm putting commas in. When we have something like this, a strict inequality, it's going to stay the same. This is where it gets really, really exciting, and here's why. This is some sort of a 4th degree quartic curve, and it's doing something on the graph, and I have no idea what it is, but it does some sort of curve, and it has that point filled in. Okay, and so if I come out here to some point in the domain, and I try to put on a tangent line, piece of cake, no problem. It works at every point, especially with that arrow on the end. It works at every point, except this one right here, because, well, that's a tangent, that only hits it once, and, well, that's a tangent, and that's a tangent. So at that end point, it's not clear what the derivative is or what the slope is. So when we go to write our derivative function, we can't claim that we know what that slope is, and so we can't include 3 in our domain. So all that happens is we exclude 3, but we retain all those other points in our domain. This is done. Okay, we'll talk a little bit about physics, and then we'll get out of here. So let's start with a position function, something that tells us where we are in space. And let's make the units of that function be miles. I'm going to call that the f function. Okay? If we took a derivative of that, we started looking at the rate of change of that, and we're looking at how our position changes, or the rate at which our position changes, what that's going to be is a velocity. So the derivative of position is going to be velocity, or speed as some people call it. Velocity is a little bit more meaningful because it includes direction. Okay? And the units of that, well, velocity, well, if it's miles, let's do one that we're really familiar with. Could be something like miles per hour. Okay? Let's keep going. The rate at which our velocity is changing. Our velocity is increasing, our velocity is decreasing, something like that. That second derivative is acceleration. And how do the units work for that? Well, that's miles per hour squared. So it's like every time we take a derivative, we are dividing by our input. Okay, that thing along the x-axis. So miles get divided by hours, get divided by hours again. Okay, now let's apply that to an example. Okay, and here it is. So I've got that same information written out here, and we're going to try our little example. So here it is. In barrel racing, we've got a rider and a horse. They're going to start from the finish line. They're going to race toward the barrel where they turn around and race back to the finish line. We got little Susie, and her position is given by a little function in here. Nice. How long does it take her to complete the course? What was her velocity 2 seconds into the race? And what is her acceleration as she crosses the finish line? Cool. Let's take a look at that. If you're not familiar with it, barrel racing has a starting line. The horses come, they race around a barrel, and they come back. And when they cross the line the first time, the time starts. When they get back the second time, the time ends. I'm going to write a position function out up here. S of t equals t squared minus 8.3t. Okay, and what that is, it's distance from the finish line. So she starts out at 0 distance from the finish line, she ends at 0 distance, she goes away from it, and then she comes back. That kind of makes sense because it's kind of a quadratic. If you flip this upside down, it would actually look like the graph. Okay, so how long did it take her to complete the course? Well, that's the zeros. Okay, let's factor this and find out. So that'd be t times t minus 8.3. Our zeros are 0 and 8.3. So she started at 0, ended at 8.3. So 8.3 seconds is how long it takes her to run the course. Okay, we're also asked about her velocity. So what is it that we're really being asked to do? Remember, if we have a position function, f prime, the derivative is the velocity function. So let's write down the velocity function. Take a derivative of this. Remember, the 2 comes in front. Subtract 1, so we get 2t. The t is going to go away. That 1's going to come in front, and then minus 1. And so we get minus 8.3. And what were we asked? We were asked, what is her velocity 2 seconds into the race? Okay, so let's plug that in. 2 times 2 minus 8.3. Alright, that's 4 minus 8.3. And so we get negative 4.3. Okay, well, what does that mean? That she has a negative velocity. All that tells us, she's running away from the finish line. She's somewhere in here. She's headed down toward that barrel. Okay, and so negative 4.3, do we have enough units to be able to write out what that means? We don't. So we're going to leave it as just negative 4.3 for right now. We were also asked about her acceleration as she crossed the finish line. Okay, so let's do acceleration. Okay, to get acceleration, it's a second derivative. We already know our first derivative. Let's find the second derivative. Okay, so constants disappear when you take a derivative, and then we have 2t. 2t is going to turn into 2. That's it. No matter what you plug in, it's 2. So we've answered that part of the question as well. Okay, this is just a brief introduction to the product rule, or excuse me, the power rule. And product rule will be next time, and we'll be taking a look at some more applications as we go. Hope you enjoyed. Have a nice day. See you next time.